yeah, I named them thick graphs. Actually, there's a list of synonyms which even in my articles appear, and depends a bit on which community you talk to. Sometimes it's good to call it very applied or to be more abstract. And actually, I mean the same thing as in the talk of Daniel Grieser yesterday. So, and let me start to present the problem and also the results. And then the second part, I will come to the methods and some consequences of the results I explain. So this basis, I'm starting from a metric graph, and I just, instead of giving any formal definition, I just draw a picture. I think at this stage of the conference this is enough. And the picture maybe says more than all the technical definitions. So this is a graph x naught. And okay, we have vertices here. I name them with small v and edges e. And yeah, let's take it finite. Here you have vertices of degree 1, it doesn't matter. And actually what I'm considering is now a sort of epsilon neighborhood of this graph. So let me draw it here. Something like this. So I'm just, if you want, if this graph is embedded in R2, just take an epsilon neighborhood. So the thickness here is just epsilon. And okay, this is not precisely drawn here. And I will later on use, let me magnificate it here a bit, otherwise you can't see. I will take these boundary, these vertex neighborhoods. I will call them x, or maybe I should write a bit higher here, x v epsilon. And, or maybe I use a color here. Let me take yellow. So this part here, I always assume that this is just isometric to some scaled fixed manifold, or space if you want, yeah? And yeah, I will always use coordinates which are epsilon independent, because we're dealing with L2 spaces and we can put all the epsilon dependencies in the metric and in the measures. Actually, you could also think about think about the epsilon neighborhood in R3. So you have the pipeline network and a full cylinder with boundary. Or you could think of the surface of this pipeline network in R3. So you have only a surface, so of the network. Or you could even define such sets abstractly by building blocks of this type here and cylinders here, and according to the graph rule. But let's keep to this simple picture here. And actually what I'm considering now, what I want to show is, I would like to show that certain operators h epsilon defined on this the thick graph, that they converge to h0. So let me put it in quotation marks, because I mean I'm dealing with different spaces, and a priori it's not clear what does it mean to say convergence of operators in different spaces. This will basically be part of my in the second part of my my talk. Let me first start with the results. So I make a list of certain operators where you can show convergence. Actually, so let h epsilon be the Neumann Laplacian. So in this setting we have a boundary here along the graph, and there we put Neumann conditions on this thick graph. And yeah, this is the simplest example. Various people have shown that this converges to, provided you have these assumptions on the neighborhoods of the vertices here, so that they are small. You can show that this converges to the Kirchhoff, or whatever you call it, Laplacian on the. I would like to use Kirchhoff here because otherwise this interferes with the Neumann condition here. They are not related. X0. And actually this is just we mentioned a few names done by Saito did some work here. Colin de Verdier did not this convergence, but at least he used similar ideas. And there, of course, works showing not the convergence of the operators, but the spectra. This is by Rubinstein, Schatzmann, and of course Peter Kutschmann and Zeng. Yeah, and myself with Pavel Exner. We showed first convergence of the spectrum, and this result, how it's written here, this is proven by me in 2006. And yeah, I come to the, I make it more precise later on, don't worry.
This convergence, in which sense?
Okay, let me say in operator norm. But I make it more precise in the second part, yes? Don't worry. I just would like to announce first the results and then say how I do it, yes? Yeah. Okay. I will define this. So, okay, yeah. So don't worry, I will explain it, yes? I come to this in a moment. In a similar setting, you can do the following. This is if you allow now a bit more general operators, so not only the Neumann Laplacian, but now you allow a potential. Oops. I do this. Now I allow a potential here. We call it Q epsilon, because V is already reserved for the vertices. And yeah, where does this potential live? Essentially, you have. Let me draw a picture here. Oh no, shit, this is not good perspective here now. Sorry for that. And actually, I'm on the neighborhood here, the vertex neighborhood. And there, I assume that my potential just lives here, for simplicity. Okay, sorry. So Q just lives here, and I assume that Q equals just the coupling constant epsilon 1 over epsilon times a fixed potential. And actually what you get then, the scaling is important here because if you do it differently, you don't get the result. You get the following operator. You get we call H0 is just the Laplacian on the graph with the delta conditions. Let me write it informally in this way. You have the sum over the vertices, and the coupling constant of the delta is given by the integral of this unscaled potential at the vertex. So QV over the unscaled version here times the delta in V. So what does delta in V means? Just to remind you, you have continuity of the functions, and the condition on the derivative is just you take the sum over all edges, and this is just let me call this small qv times the value at the function. Yeah, this is just a delta coupling. There might enter another constant here due to this normalization, but roughly this is it. And yeah, this was shown by recently by Pavel Exner and me. Yeah, I think it appears last year. Okay, and Okay, I don't want to bore you with all these things you can do in this setting, because you will see later on that the arguments are always very similar. We mentioned a last result of this type. If you take, again, only a pure Laplacian x epsilon, but now you allow a sort of Robin type condition. And okay, what Robin conditions do I mean? Let me draw again a part of this thick graph. And actually, I would like to impose conditions here. So on this set here, this should be green. On this part, okay, what are Robin conditions? Actually, I just assume that the normal derivative equals some function beta epsilon u on the boundary of my thick graph, yes? So the boundary in this setting is just here, the lines you see here. And on the green part, so close to this neighborhood here, let me call this gamma v epsilon. This is just, again, by scaling invariance epsilon times a fixed set, because of my basic assumption there. And you have here, we want the function to be of order 1 on this set here. So there you get some contribution, which you will see later on. And on the other part, this is important now, you take some, you want it to be small, to the power epsilon, to the power 1 plus eta, actually on the other set here, on this part. Oh, sorry. On, let me call this edge boundary. So I could call this one, if this is edge E, I could call this one E epsilon. And actually, if you know the results, I mean, I didn't make a comment on how my results are related now to the results of yesterday. The basic difference is, to the talk of yesterday, is that Daniel considered general conditions here, for example, Dirichlet. And my basic assumption is I use Neumann conditions, or if I have no boundary, no conditions, and that the lowest transversal eigenmode is just constant. Yeah. So you can just take, you see here, the lowest eigenfunction in this transversal set here is just a constant function, so the eigenmode is 0. And if you, for example, take Robin conditions, the natural scaling would be that beta epsilon scales over 1 over epsilon. And then, of course, you get divergent terms. But if you do it in this way, you see that there's no contribution on the edges. And what comes out as result is just, again, you get a sort of the Laplacian and delta conditions. And now the couplings are given by the integral over this beta on this green part here. Beta v and times delta v. So just the green part, and this assumption here is made in order to don't have any contributions on the edges. If you want, in this setting, the lowest eigenvalue and eigenmode are close to the Neumann one. They're close to the constant function, and the lowest eigenmode is close to is close to 0. Okay. Sorry? Ah, yeah. Sorry. Of course, yeah. Yeah. Yeah.
Draw this green stat as if it's smooth, but actually it's not good. If it's strictly defined by an epsilon neighborhood.
Ah, you're right. Sorry, I mentioned, yeah. I said here I take an epsilon neighborhood actually to give you an idea. You can do both. You can smooth it out, you can take it really as epsilon neighborhood to have corners here. And okay, you don't want to be the corners to be too bad because you still need that the Neumann problem is somehow defined. You don't want any essential spectrum coming from the boundary, of course. So let's assume it's smooth, yeah?
So you're saying that the results do not depend upon the way that you smooth it out?
This result doesn't depend on, this is very stable. You can do anything here. Just once you know that your neighborhood is just scales in the right way. And yeah, actually I think we assume smoothness here. Yeah, this, I'm not sure if you take a weird domain, you might get in trouble here, yes. But let's assume it's smooth, yeah? But actually the results are pretty stable. Yeah, and let me make one comment on the talk this morning by Professor Fueling. Actually, there was one idea why I was interested in this index properties of quantum graphs, because one idea was I wanted to know which boundary conditions can be approximated by a pure Laplacian, and I wanted to see whether this can be seen by the index of some operators, because indices are normally very stable. So, and there was one idea that one cannot approximate a delta condition by pure geometry. So in this way, here only you see here we need the potential to get delta, and here we need something on the boundary with Robin conditions. Okay, I think it's now time for explaining what do I mean by the convergence. Actually, oh sorry, I didn't make credits to this point here. This is a recent result by Munulo, Nitka, and myself. It's just published, I think, last week on Archive. Actually, to be more precise, this was just our main example in this paper. We basically did something more general on sectorial operators, what I explain now in part 2 for self-adjoint operators. Okay. Yeah, let me come now to the methods. And consequences. Actually, what do I mean by the statement that the operators converge? And this is just a very simple, let me do it in a very simple setting. You can do it more generally, but I don't want to introduce too much notation. Different Hilbert spaces. Actually, let me define what I mean by this convergence. So assume we have operators H indexed by a parameter epsilon, and they are non-negative. For epsilon, 0 is allowed for the limit, and this is an operator in Hilbert space H epsilon. And actually it's unbounded like my example here. And what do I mean by H epsilon converges to H0? This is defined in the following way. Two conditions. The first one is, or actually I need one thing before. There exists an operator J, which is a sort of identification operator which interpolates between, which says somehow how should I relate these two spaces. So actually it depends on on epsilon, and it starts from the Hilbert space 0. So in my example from the graph, and goes to the thick graph, L2 space over this here, such that I have two conditions. Actually, the first one is the following. I want that J somehow is close to a unitary operator. Of course, I cannot expect this to be unitary because the problems are very different. But what I can assume is the following. I want that if I take the condition for unitarity, I want it to be fulfilled in a limit, yes? And in order to do this, I need to smooth it out a bit by make it better here by a resolvent. And I take operator norm, and I want this to converge to 0. And actually, R is just a resolvent for epsilon bigger than 0. Because my operators are strictly non-negative, so I can just take -1 in the resolvent. And this is one condition, and the symmetric one, of course, too. The other one is just this way around. I give in a moment an example what operator I use in this example. Yes, just let me write down the second condition, because this is just a condition on J up to the smoothing here. So this I could call quasi unitary, if you want. And now I want something like a quasi intertwining property for this J. This just means that if I take the resolvent on the thick graph, I have to put the sandwich with J minus J resolvent on the graph. And this operator norm should also converge to 0 as epsilon goes to 0. I could call this a quasi intertwining, if you want. Why quasi or approximately? If this would be exactly 0, you see these are just the conditions for unitarity, and if this is 0, this is just condition that J intertwines the two operators, yes? And now the question, because I have unbound operators, I need to do this for the resolvents. Actually, let me give an example. And since I'm dealing with problems which are all related to the Neumann problem, actually I have, in the first case, it's really Neumann boundary condition, in the second one too, and the third, I told you that on the edges we are close to the Neumann problem because the lowest transversal mode is very, very small. We can use the same J in all these examples. And actually what I do, let me again just draw a picture how it looks like. We take a function f, so this is on x0. We take a function here, use some color, maybe yellow. I take a function which is just, this is he1, fe1, a function here. Okay, maybe it's continuous, whatever. A priori it's only in L2. And what does the map J do with this function? Well, we get a function jf on my thick graph. And actually, I try to draw it here. I just try to squeeze it here to make it, of course, transversally constant, because the lowest eigenmode is constant or approximately constant. And I just take the same shape of the function here. If there might be a small error happening here because of this neighborhood here, you just squeeze it in a way that it fits exactly, yes? This is not the point. Here, or you could write, you take the function e1 tensor phi e1. This is just a constant. In this case, in the talk of Daniel, this would have been just the lowest eigenvalue eigenfunction on the interval Dirichlet problem. And you do the same here, just like this. And similarly here. Oh, too many colors here. I think hopefully it's still readable from the last line, from the last row. And actually, I set it to be 0 here. This looks a priori a bit bad, because you think, why should I make it a very rough estimate here? But if you think a little bit about it, I'm starting with functions on this base here, which are only in L2. So I don't know I cannot talk about the value of the function here in a L2 space, even not in an interval. And yeah, I'll come to this point in a moment. What does the adjoint do? This is also not too complicated to see it. It just takes an arbitrary function, forgets about what's happening in this part here, and it just, if you have here just a function which is just some sort of whittling around in the transversal direction, then you just take the average of this function here at the value. So just take the average here, so this is just the coefficient of the constant eigenfunction. You could call it transversal average. Average if you want. Yeah, and in my examples here, I just have, yeah, maybe I write it here. Oh, I can write it here. In the examples, oh, I think I have to erase something here. Actually, where did I put? Ah. Yeah, I mean what I said about this a bit rough approximation, if you do a similar argument for the spaces of order 1, for the Sobolev spaces of order 1, so in the Kirchhoff case, this is just the functions in H1 on the intervals and just continuous here, and here's just the usual Sobolev space of order 1. You know what it means to evaluate the function at a point, and then you can really take the common value here as a constant. And actually, the results are proven in a way that we use the first order identification operators, but this needs much more notation, and I would like to just keep on this picture here. And actually you can prove it also in this way. Yeah, what's happening here? I have to check these conditions here, 1 and 2, and actually the first one is very easy to see. If I take a function and embed it in this way on this thick graph, and then take the transversal average again back, you end up with the same value because you don't lose any information. This is very easily seen. And the other way around, of course, there you lose something. And what's happening here? Yeah, actually what you do is you take a function here, project onto the transversal eigenmode here, and then go back. Then you see you lose information what's happening on this vertex neighborhood. So you lose the, so this is just remains here what's happening on the scale small neighborhoods here. This is just not seen if you go from here to here and back. And what's happening on the edges is just, yeah, well, you just get u minus, because you project onto the lowest eigenmode, you have to subtract it here. Let me write it this way, just the average integral. This just means the projection onto transversal constant function. And well, I mean, I don't want to give the proof in detail, of course, but just give an idea what's happening now. You know that functions which are in a bounded spectral interval, because you always have, if epsilon goes to 0, you always have high eigenmodes which just go up to infinity, the eigenvalues. But if you have a family of eigenfunctions which stay in a bounded interval with respect to epsilon, then you have no concentration at these vertex neighborhoods here. And basically you need the assumption here, what I did here, that this is just shrinking to, if epsilon goes to 0. And actually you can just do it a bit more general, and you see the critical parameter is just the volume of the set divided by the transversal volume here. So in this case, this would just be epsilon squared, and here is epsilon. So the critical parameter would just be if this is just escaped by another parameter, just if this is of order epsilon here. Take the parameter here to be square root of epsilon here. Okay. So you have no concentration there, and again the same thing for at higher eigenmodes. It is easily seen that if you want the family to be bounded, to be the family of eigenfunctions to be in a bounded interval, then this can never be finite here. Yeah, this just explodes. And yeah, actually, what you can do then, show then that the above thing here is just bounded by some O of epsilon times the gradient of u plus the norm, something like this, of this form. Yeah, there's some relation. I mean, compared to the work of Daniel Grieser, it's I only get here the error to be epsilon. So for the operator norm later on is square root of epsilon if I take the square roots here. And it seems that my methods are too weak to give more information. I mean, it's just a very rough estimate I used there, and it's pretty stable. But of course, you can expect to show very strong results then if you use weak assumptions. Yeah, actually, maybe I can't see him, but maybe you can. Where's the guy? I think he should hear me. I just want to show some consequences on the with the computer, but I need the projector. yeah, he's doing it there. Okay. Should have given him a sign, but okay. How much time? Some minutes, yes? 10 or 11. Oh, okay. Yeah, okay. I don't want to take too much time, so I'm waiting for the... yeah, good. Actually, this is not the whole presentation again. Just... no. Now everything in a quick slideshow. No. No, page down, yeah. Okay. Let me just say something about the consequence of the convergence. It's just now hidden now here, but hopefully you still remember. What you can do it very just in this abstract setting, and then you can show, for example, that take a function of the operators, sandwiches with j, and this converges to 0. For example, for the heat operator, or for spectral projectors. For suitable functions, actually you need something like this limit exists, so you cannot expect this to hold for the unitary group. Yeah, this doesn't work. And you can show similarly sandwiches another way. Take phi of the function on the graph, and you take the one on the manifold. On the thick graph and on the graph. And actually, this is in a way interesting because now, I mean, we have formulas, for example, for the heat operator on the metric graph. We have formulas. We can just write it mostly explicitly down. And then we take our operators j star and j, and actually we get a good approximation of what's happening on the manifold. And I think this is and something which is cannot be seen by direct methods maybe. This is one consequence. Yeah, and under certain assumptions, I mentioned the recent article with Delio Muniolo and Robin Nitka and myself. We can even prove convergence in LP. We need some more assumptions which are fulfilled in our model here. And actually, this abstract convergence, I mean, what you do if you have this condition here, you start to repeat everything what's done for convergence of operators, the consequences like convergence of spectra in this setting. You have to be a bit careful because now you have only a weaker assumption with this J and J star. It's not even J doesn't have to be bijective, of course. It isn't in our case. And yeah, we get the conversion of the spectrum. This has been shown by other methods, by variational methods before, by Rubinstein, Schatzmann, Kurzman, Zeng, and yeah, a bit generalized by myself and Pavel Exner. And also the old article of Colin de Verdière, where it's implicitly used. But for example, what we can do now also is just is there some free? Maybe I can draw it here. Hopefully you can see it. So think of here I write the spectrum of H epsilon, and here is epsilon. And assume you have a sort of you have a spectral. No, this doesn't work. Let's take this color. You have some. You have here a spectral gap and a set of eigenvalue in the gap. Yes.
So you're thinking of a perturbation of an infinite periodic graph.
For example, yes. You can do it this way. You have an eigenvalue, and it's very easy to construct eigenvalues, or say you have a periodic graph and you take a perturbation. It's very easy to produce such eigenstates by just adding some sort of loops, and it's not difficult to do. And then you have, for your approximating problem, on your manifold, you just have something which is, the gap is close to it. So this here maybe is like this. And you still have an eigenvalue here. So some function, some eigenvalue converging here, and you also have convergence of the eigenfunctions in this way. And actually you can go a bit before, and if you have just a graph with a gap in the essential spectrum, since you know that the essential spectrum also converges uniformly in just bounded intervals, energy parts, you know that your fig graph also has a spectral gap, yes, just by the convergence. And let me give just one funny example. You can't. Oh, this is not readable here. I have to explain it. So, the Sierpinski graph. So you take a non-compact metric graph. So I just take the. So think of, maybe you can't see it here, but these are the vertices here of this graph, and you have edges here which are all of length 1. So the graph is non-compact. It's going up to infinity. It's not the process that it's being compacted, but the other way around. You expand it. And since all the edges have the same length, you have a nice spectral relation to the discrete Laplacian. And then we know by the results of Sasha Teblayev that the spectrum of the discrete Laplacian has fractal nature. The same is true for the corresponding metric Laplacians. And what you can do now is you take an approximation of this metric graph by a thick graph, for example, some pipeline network or just some epsilon neighborhood here in this way. And what you get is now that the number of components in each compact interval just tends to infinity, because in the limit it's a Cantor set and it has infinitely many components. Of course, the methods are pretty weak, so I cannot say anything about the nature of the spectrum of H epsilon itself, because one expects maybe that it's also a fractal spectrum, but I can only show a sort of convergence. Yeah, so I don't know whether actually there are infinitely many gaps or not. And well, yeah, some literature. I think maybe I leave it there. Let me just. Yeah, I think there's not much time left, but let me just make a picture for one result I announced, at least in the statement. So this is why there are also citations of the boundary triple. Okay, we have a graph x0 here, and I declare now as boundary, let's take these vertices here. This is just the boundary of x0. And again, I take my favorite thick graph. Like this, as before, x epsilon, and the boundary again. Okay, this is a bit different from the notation. Yeah, maybe I should give it a different name, maybe boundary 0 or something like this. Because as boundary, I want now only to see this as a boundary part. And whatever happens here is just remains the same, like Neumann conditions, yeah? And what I want to do now is just to solve to define the derivative to Neumann map. At a certain point. So what I do, I just fix values here. Yeah, you take a function phi here on the boundary, and then you solve just the Neumann problem by just saying that H is solution, the Dirichlet problem of minus the Laplacian minus plus 1 H0, and you want H to be equal to phi on the boundary. So actually what I'm doing, if I draw a picture, I just fix the values here and then I solve, okay, I get sort of functions which are just maybe whatever they're doing here. Has to fulfill Kirchhoff inside here, my function h. And then I take the derivatives here. So lambda 0 of phi is now the derivative of f at the of h at the boundary. And actually I'm doing the same thing on the manifold, just fixing a function here, fixing a function here, fixing a function here, and then okay, we solve the Dirichlet problem somehow. Just get a function here. And again, lambda epsilon, phi epsilon equals just now in this case a normal derivative. And actually what we can show now in a similar spirit as I explained here with identification operators, this is a joint work with UC Bernd from the Technical University of Berlin. What we showed in this case is that the Dirichlet normal operator of this set converges to the one on the graph. So actually what you do is you can approximate this pseudo-differential operator of order 1 with just a discrete matrix, with just a matrix in this case of 3 components. And of course what you do in a similar way, you just project onto the lowest eigenmodes. This is the reason actually you only look at the lower spectrum. And yeah, I think I don't have time to explain the details. Let me just mention one thing which related to the talk yesterday of Bob Carlson, that I also define the derivative to Neumann map in an abstract way via the sort of the energy of the Dirichlet solution. So just via form methods. And this is just the key in order to use all these results I explained before to solve this problem. Yeah, I think my time is up, and thank you for your attention.